Good. Thank you so much for having me. It's really a pleasure to be here and to talk to you about this topic that I think has captivated many of us for a long time. And I will jump right into it. So I think that the Earth's place in the cosmos is something that has been discussed for as long as we have had recorded history. I think one of the most lasting ideas about Earth's place comes from Ptolemy, who thought incorrectly that Earth was the center of the universe. You can see his little diagram here with Earth in the middle and then all of the planets orbiting in perfect circles around it. This was considered to be very elegant in Greek philosophy. Circles were the most ideal of forms. Of course, it was also incorrect, and so they had to introduce all these fudge factors. You might have heard of epicycles, which were little circles within circles to try to get the theory to work out if you cared about something like where Venus was going to be 2 weeks from now. So as a marker of scientific success, I think how long your theory sticks around is often considered good. In this case, that does not apply because it was over a millennium later that finally the mood shifted and scientists began to realize that the Earth was not the center of the universe, but rather the sun, at least in our solar system, was the center, and all of the planets, including the Earth, were orbiting it. This was famously attributed to Copernicus. I think he's the most renowned for this idea. It was also discussed by some Persian astronomers a couple hundred years earlier. But to give some perspective about how not only revolutionary but also heretical this idea was at the time, Copernicus had a buddy who was editing his manuscript, and he decided to put at the beginning this little disclaimer that said, no, we don't really know if, we're not saying this is necessarily correct, this idea that the sun is the center of the solar system. It just happens to explain everything we've ever observed. And then they dedicated it to the Pope. So I think Copernicus played that much better than Galileo did after him. But, although this was really a huge paradigm shift in the thinking, it took off and inspired a lot of other areas of scientific inquiry. It was thought to have inspired Isaac Newton and even Einstein later on, who extended this idea that not about the Earth not being the center of the universe, but rather that the Earth is not special in any way, and that the laws of physics should be the same everywhere, and that we can study those in a systematic way, not from any privileged vantage point from here on Earth. So that was 500 years ago. And excitingly, just in 1995, so like basically yesterday, we have embarked on a new journey in our attempt to understand where Earth fits in the cosmos. And this is, of course, the discovery of extrasolar planets orbiting other stars. I love this picture of the two co-discoverers of the first planet around a main sequence star. Didier Queloz in the corner there was just a grad student. You can see how excited he was. Actually, I saw him a couple weeks ago, and I put this slide in my talk specifically to tease him a little bit because I thought he would be embarrassed to have his name up there on a slide with Ptolemy and Copernicus, and I was correct. He has a Nobel Prize now, so nobody makes fun of him, but I think people still should. All right, I see the exoplanet folks in the audience nodding. Yes, that's right. All right, so without further ado, how do we actually detect planets around other stars? And there's a bunch of different techniques, but these are two of the most common ones. The first I'm illustrating with an animation up at the top. This is the radial velocity method. And the key idea here is that the planet's gravity tugs on the star a little bit over the course of its orbit and causes the star to move back and forth. And as it moves, the light that it emits is Doppler shifted, just as the sound of an ambulance might sound a little higher pitched as it moves towards you and a little lower pitched as it moves away from you. And this method is sensitive to the mass of the planet and also its orbital period, so how long it takes to go around the star. The second technique, which is even more popular, is called the transit method. And this happens for very lucky cases when the geometry just works out so that the planet happens to pass in front of the star along our line of sight. And during a transit, a little bit of the starlight is blocked. Something like 1% of the light would be blocked for a Jupiter-sized planet around a star like the Sun. But Earth, of course, is much smaller, and so in that case, it's something like less than 1/100th of a percent, so really small signal. Oops. You can also, as a preview for what we'll see later, you can also see in this cartoon some sinusoidal variation. This is when you have a planet that is tidally locked to its host star, so it has a hot side and a cold side. As it moves through its orbit, if you measure the heat coming from the star plus the planet, you can actually tell these differences of how the temperature of the planet that you're observing and how that changes with longitude. We'll come back to this later. Okay. So exoplanets are extremely common. Since in the 30 years that we have been searching for them, we found almost 6,000. And most of these are very nearby. We have just looked at the very tip of the iceberg of what is out there. You can see in this diagram the number of planets discovered every year. They're color-coded by their detection methods. So these purple ones are the transiting planets. The green ones are the radial velocity planets, and then there's a smattering of other cases. And I happened to be standing in line at a conference with Lord Martin Rees, who is currently the Astronomer Royal. I don't know exactly what that job means, but I think it's something like you get to talk to the ghost of Isaac Newton or something like that. And so I was a grad student, I was really scared. I was like, oh no, I have to make small talk with Lord Martin, what do I say? And he very kindly, he saw that I was scared and he just said, what do you work on? And I told him, I work on exoplanets. And he just sort of, he nodded and he said, a Copernican demotion of the grandest scale. And I thought I really needed to work on my small talk after that. But it stuck with me because he was totally right. I mean, I think prior to 1995, a lot of people had thought about whether there might be planets around other stars, but nobody knew for sure. And so there was this illusion that maybe there was something special about the solar system. And now that we see that, stars are just lousy with planets, that really puts a different perspective on how special the Earth actually is. Here's some statistics. So this is one of the most famous diagrams from, I would say, the last 30 years of exoplanets. This is showing essentially the head count of how many planets there are as a function of size for periods within 100 days, so fairly close to their host stars. And you can see a bunch of things from this plot. So you can see, first of all, that these smaller planets over here are much more common than the large ones. So planets that are approximately Neptune size and smaller, that's roughly 4 times the radius of the Earth, are about 10 times more common than gas giants like Saturn and Jupiter, which would live out here. You can also see that there are 2 peaks. We think that these correspond to truly terrestrial planets. So these are rocky things like the Earth that have a solid surface, that have bulk composition dominated by iron and rock. And then there's also these things over here that are still quite a puzzle. People are arguing about what to call these. Some people call them mini-Neptunes, sub-Neptunes, gas dwarfs. For a while, I was really pushing hard for Neptini, and it never took off. I'll keep trying, though. But the point is that these ones, these rocky planets, are extremely common. We think that something like 10 to 20% of stars host a planet that is approximately the same size and the same mass as the Earth, and have similar temperatures where liquid water could exist. Given that, the fact that there are hundreds of billions of stars in the Milky Way, that puts us at something like tens of billions of potentially habitable planets in our galaxy alone. Okay. Yes, I put this on here as a reminder to myself in case I got too distracted by the previous slide. Earth-like planets are extremely common. That's one of the big messages I want you guys to take away from this talk. Okay. But what does Earth-like actually mean? So I just told you that if you're looking at planets that are approximately the size of the Earth, the temperature of the Earth, there's tens of billions of those. But a rock at an Earth temperature does not a habitable planet make. And you can tell that very clearly just by looking at pictures. So Earth has water, it has clouds, it has plate tectonics, it has continents, it has a nice atmosphere. And at the level of detail that we've been able to observe most of these exoplanets, we can't tell the difference between a planet that is truly like Earth, with a nice atmosphere and all kinds of good material if you want to make life out of it, versus a bare rock. And so that's where astronomers are trying to take the next step to actually characterize the atmospheres of these planets to tell the difference between a bare rock scenario, something like the Moon or Mercury, and a planet that is truly like Earth. So, as just a brief primer of how we learn about the atmospheres of exoplanets, one of the most common approaches at the moment is to look at these planets that are transiting, so they have this special geometry where the planet passes in front of the star. And when that happens, during a transit, a little bit of the starlight will filter through the planet's atmosphere where it can be absorbed or scattered by the molecules that are present there. And so at wavelengths or colors of light, where the atmosphere is more opaque, the planet appears to be just a little bit bigger. Whereas at wavelengths where it's more transparent, it appears to be a little bit smaller. And so if you measure the size of the planet as a function of wavelength, you can work backwards to infer what the chemical makeup of its atmosphere is. Okay. So to make this a little bit more intuitive, I really like to show these images of Earth taken from space. Here's what Earth would look like to your eyes. So this is optical light. You can see, if you look carefully, this little blue rim right here. That's Rayleigh scattering. That's what makes the sky look blue. But if you move to the infrared, the Earth looks a little bit smaller. So that Rayleigh scattering signature, that blue sky, is gone. See that? But if you move just a little bit farther into the infrared, Earth looks a little bit bigger again. And that is the smoking gun signature of ozone in Earth's atmosphere. Ozone happens to be very opaque at this particular wavelength, and you can see that in how much bigger the Earth looks. Now, of course, this is super easy to do if you fly a nice satellite right over the Earth. If you're trying to do this for an exoplanet that is tens or hundreds of light years away, it's a much more difficult thing. But this is the goal. This is the type of thing we're trying to see. So here is a model of what these size variations should look like for the Earth. So you can think of the y-axis here is the size of the planet, bigger is up. And then we have wavelength here on the x-axis, so blue to red. And these different peaks are color-coded based on which molecule is responsible for the absorption. So you can see really clearly here there's a huge peak from carbon dioxide. This over here is ozone. You can see some features from methane as well. I think those are in, where are those? Those are in yellow, so here's a methane feature here. And if you were an alien observer looking at the Earth from afar and you saw a spectrum like this, you would know immediately that something was up. And the reason for that is that we have in our atmosphere both oxygen and methane together. And these two molecules really want to react with each other to form something else. They're very unstable. And so the fact that we see them in abundance in our atmosphere means that there must be some constant source of production that is keeping enough oxygen and enough methane high up in the atmosphere where we can observe it. And you could scratch your head and say, well, is there any other way you could do that? Could you have photochemistry? Could you have volcanoes? And there's a lot of different possibilities, but basically, no matter how hard you think about it, it's very, very, very tough to get this particular combination of molecules in the atmosphere of a planet that doesn't have life on it. We often call these biosignatures, and I'm talking about oxygen and methane here. That's the classic example on Earth. There's a lot of other ideas about different molecular pairs that would not exist in chemical equilibrium that could be a possible signpost for life. So, starting easy, before we get to Earth-sized planets, I want to talk a little bit about hot Jupiters. These are the easiest possible exoplanets for us to characterize from far away. We have been practicing on these for several decades now, and this is one of the best examples from about 5 years ago. This is real data, so the black points with error bars were measured with the Hubble Space Telescope. You can see those compared to an atmosphere model. Those are the colored lines. And just like in the cartoon, you can see these very clear peaks from different molecules. In this case, this is water. And that's already exciting, actually. So before I started working on exoplanets, I had no clue how common water was in the solar system or in the galaxy. And it turns out water is all over the place. After hydrogen and helium, carbon, nitrogen, and oxygen are the most abundant elements. And at the temperatures and pressures on a typical planet, that oxygen and hydrogen really wants to be in the form of water. So we've discovered water in the atmospheres of a whole bunch of gas giants. And this is a nice example. So that was pre-JWST. And now I'm going to take you to post. So I think probably most folks in the audience have heard of this telescope, the James Webb Space Telescope, that was successfully launched on Christmas Day of 2021. I think a lot of people thought of this as a Christmas present, but I was actually like a nervous wreck because I wasn't sure if it was going to work or not. Luckily, it did. Here is an animation of the telescope unfolding in space. It operates in the infrared, and so it has to have a big shield to protect the very sensitive instruments from heat from the sun. So you can see that sun shield unfolding here. I kind of think of this as one of those like foil things that you put in the window of your car on a hot summer day. Just a lot more expensive version of that. So here it's carefully unfolding. This had to happen perfectly because this telescope is so far away that it couldn't be there. We couldn't send a servicing mission to fix it in case anything went wrong. So beautifully done, perfectly unfolding. There were something like 300 single point failures in this process. You might wonder that was the scary part. Went great. I'm like nervous about this. I'm like post-nervous about this. This is so scary. All right, there's the primary mirror starting to unfold. All of this origami that happened was because there was no rocket that was big enough that the entire unfolded telescope could fit. And so they had to fold it up and then perfectly unfold it in space after going through a launch. So it was a really amazing thing. This is one of the most sophisticated instruments that humanity has ever built. And everybody loves a good before and after, so I'll show you one here. I'm going to zoom in to this part of the spectrum that has the red box around it. This is what it looked like prior to JWST. And now, once the telescope launched, one of the very first things we did was to point it at this particular planet. We knew that it had nice spectral features. It was an easy case to test our methods on. This is what we got. That is so awesome. This here, this big bump here, this is carbon dioxide. This is the first time carbon dioxide was ever detected in a planet outside of the solar system. And you can see it, for non-experts in the room, this is almost as if you walk down the street and you see an old friend, and of course you recognize them, you know what it looks like. When this carbon dioxide feature came out, I was talking to one of my colleagues and I asked him how he was feeling. Was he excited about it? And, just catching up. And he's like, God, this data looks so good. I thought it was fake. He was also, by the way, the same person who was complaining when our data looked like that. So clearly this is someone who just can't be pleased no matter what. Okay. We'll just do this again. Yes. Amazing. Okay. Good. So now, thanks to the huge advance in observing capabilities from JWST, it's possible to begin pushing these observing methods to smaller planets, to cooler planets that are closer to the Earth. And for the rest of the talk, a little bit more introduction, then I'll actually show you some stuff. So where do we start? It is fairly straightforward that if you are measuring the size of the planet relative to the star, that's all of these measurements are relative to the star, it's easier to do if your star is smaller. And actually, most of the stars in the galaxy are much smaller than the sun. We call these things M-dwarfs. They're cooler, redder, fainter than the sun. And they also happen to host a lot of rocky planets. And so not only are these M-dwarf planets easier to study, but there are also more of them. So actually most of the rocky planets in the galaxy are systems like this, the Earth around an M-dwarf, compared to the Earth around the sun. Now I'm showing a picture of a scientist named Dave Charbonneau here. Dave has really been the father of he calls it the small star opportunity. He discovered some of the very first rocky planets around these small stars. And he's been a good colleague and mentor to me for a long time, so I wanted to give him credit for really pushing this as the direction that we want to go in. So a question is, how do we even start to do this? Because even if you look at the rocky planets in the solar system, you see a ton of diversity. We have some planets that have essentially no atmosphere, like Mercury. We've got planets with a thick carbon dioxide atmosphere, like Venus. We have Earth. Our atmosphere is mostly nitrogen and oxygen, with a little bit of water and CO2. Mars has a little bit of an atmosphere. I got in trouble once with the planetary science because I said Mars doesn't have an atmosphere, and this is someone who'd spent their entire career working on the atmosphere of Mars. So I don't say that anymore. But it is very thin. It's less than 10% the surface pressure of the Earth. This is an interesting case over here. This one. Does anyone recognize that? Titan, yeah. Yeah, so Titan is a moon of Saturn that has a really interesting atmosphere. It's made mostly out of methane. And it has rather than a hydrological cycle, it has a methenological, sorry, I don't know what this word is supposed to be. It has a methane cycle where you have clouds of methane condensation, it rains out, it has methane, rivers and lakes. And even Pluto, this image on the far right is from New Horizons. Even Pluto has a little bit of an atmosphere of its own. It's very thin. It's made mostly out of nitrogen, but it has rich chemistry. It has haze layers. We think it might collapse and then reinflate as the temperature on Pluto changes. And so basically, the lesson learned from the solar system is that we should expect diversity. So wide range of surface pressures, wide range of chemical makeup. And so while there is a lot of excitement about looking for these biosignature gases, like the smoking gun signpost of life, what I've been saying recently is we really need to learn to walk before we can run. Like, we don't know if these planets even have atmospheres at all. And so that is step one. That is the main focus of my research at the moment, and what I'm going to spend probably most of the rest of the talk sharing with you. Okay, are you ready? I'm finally going to get into it. Yes. Okay. Good. So the first thing I want to share with you is the current record holder for the smallest planet that has a detected atmosphere. You ready? Okay, let's see it. Boom, there it is. So to me, this is beautiful. I was so excited when I saw this. So you see all of these different features. I've noted there which molecules they match up with. So you see a whole bunch of methane there. You see carbon dioxide. We see sulfur dioxide and maybe CS2. We think those are produced by photochemistry in the atmosphere. So it didn't match our predictions from theoretical models. And with data like this, we can actually work out sort of the underlying chemical makeup of the atmosphere. And what we found is that it's about 3 parts hydrogen, 2 parts carbon, and 1 part oxygen. Amazing, amazing that we can measure this. We also learned from this measurement that this is not actually a rocky planet. So it's small. It's only 2.1 times the radius of the Earth, so it's really little. It's 5 times smaller than these big Jupiter-like gas giants. But it's still not small enough that it's dominated by iron and rock. It has to have a pretty thick envelope of hydrogen on top. And what that means, if you have too much hydrogen in your atmosphere, it acts as like a big, heavy blanket on your planet. And as you go deeper and deeper into the atmosphere, it gets hotter and the pressure goes up. And so by the time you reach the rock layer, it's actually so hot and such high pressure that that rock is molten. And so this is a magma ocean interface with a hydrogen atmosphere on top. We don't have anything exactly like this in the solar system. But it sure ain't Earth-like. So this, like, you do not want to try to go to this planet and live on it. There's no surface. It has raised a lot of questions about whether you could have a planet kind of like this that has maybe a special layer that is appropriate for water to be in liquid form. So maybe you could have somewhere in there a water ocean. Everybody's fighting about this right now, so I'm not going to take any. This is being recorded, so I'm not going to, like, maybe over drinks later you can ask me what I really think about it. But suffice it to say, for this particular planet, we think that that is not the case. And rather, what we've got is something a little bit more like Uranus or Neptune that lands you on a molten rock layer instead of a surface. Okay. So if we really want to get to these truly rocky planets, it's a lot harder. So here's our spectral features for Earth. And if you take the hydrogen out of the atmosphere, it shrinks the vertical extent by a lot. This is because hydrogen is very light. Hydrogen atom has just 1 proton, so it likes to float. And that means that the atmospheres of these hydrogen-rich planets are much puffier than the atmospheres of a true Earth analog. And so if you want to detect that, you have to have a much more precise measurement, which is really pushing the limits even of what we can do with JWST. So this is, as of today, the current record holder of the most precise spectrum for a truly rocky planet. And I'll be direct with you, we're not there yet. I was hoping when I agreed to give this talk that we would definitely have detected spectral features with this technique. We have not yet, that's the truth. You can see here, this is the extent going from sort of bottom to top of what we would expect for an Earth-like atmosphere. I put that same gray box here compared to our data, and you can see that there's so much scatter in those data points that we have no chance of being able to detect even a relatively large feature like carbon dioxide. And that's okay, like, we just started. This is a brand new telescope, we're working on it, we're learning how it like the best way to use it. With more time and more investment and working with the data, I think we will get there, but we haven't yet. I'm not always a very patient person, so I have thought a lot about, while we are working a way to, improve our measurement precision and really get down to the level we need to detect features for a true Earth analog, is there something else that we can do that's kind of a shortcut that can answer the question of whether the planets have atmospheres at all sooner? And so I'd like to share with you my favorite technique for doing this. I'm going to go back to our cartoon of a transiting planet. The planet is tidally locked to its star, so it's very close. It has a hot day side and a cold night side. As it orbits around, you can see here the increase in brightness. Here the planet is going behind the star, so any of the heat coming from the surface or the atmosphere is blocked. And now here the hot day side is rotating out of view. And the reason this is useful is that thick atmospheres are good at recirculating heat. And so if you put a Venus-like atmosphere on this planet, those two hemispheres would have almost the same temperature. But if you have a bare rock, there's no atmosphere to help blow that hot air around to the night side. And that gives you a maximally hot day side and a night side that is essentially zero. Is this making sense? Okay. I'm a professor in my heart, so I got to check in with you guys. Okay, this is important. This is the key to interpreting the measurements that I'm going to show you now. So the way to think about it is with this extremely scientific atmosphere rating system, a 3 chili pepper planet has the hottest possible day side. That means no atmosphere. If you got 2 chili peppers, you're a little intermediate. You could have some atmosphere on the planet, but it has to be a sort of special one. It can't be too thick, and it can't have too much carbon dioxide in it. Carbon dioxide is really good at absorbing photons, as we have learned from global warming here on the Earth. And so it is also one of the things that is easiest to see for exoplanets. And then if you've got a 1 chili pepper planet, that actually corresponds to the lowest temperature, which would be characteristic of a carbon dioxide-rich atmosphere. I want to clarify something quickly. I've gotten a lot of questions about why does CO2 mean cold, because we usually think CO2 means hot. The reason for that is that we're not seeing all the way down to the surface. So the CO2 does heat up the surface, just like it does here on Earth. But our observations are only looking at the tippy top of the atmosphere, and it's colder up there if there's a lot of carbon dioxide. Okay, now you guys are all experts. Let's rate some planets. So one of the very first planetary systems that JWST observed with this technique is called TRAPPIST-1. I'm curious, actually, how many of you have heard of TRAPPIST-1? A bunch. Okay. No worries if you haven't. This is one of my favorite planetary systems. It has 7 rocky planets orbiting a nearby ultra-cool dwarf star. The star is so small that it's actually about the same size as Jupiter. And so that means that it's much cooler. The planets are much closer in than the solar system planets are to the sun. But 3 of them, E, F, and G, are in this green region here, which is used to show the region around the star where the planets could have a temperature appropriate for liquid water. So this is really exciting because these are some of the easiest planets to characterize. 3 of them could, potentially host life if we're getting way ahead of ourselves. There's also a Venus analog, so planet C is almost exactly the same size and same temperature as Venus. And so it really allows us to do comparative planetology between our own solar system and some exoplanets. This is just to show how big of a deal TRAPPIST-1 is. You know you made it if you got to the Google Doodle. And I think this also shows, right, like, this is so exciting. Like, I think in contrast to many other areas of science, there's a lot of emotional investment in this topic that makes it sometimes difficult to be objective. But we do our best. My favorite here is the moon. Yay! All right. Good. So naturally, this was one of the very, very first targets for JWST observations right after it launched. And this is it. So this is one of those figures that makes the hair on the back of my neck stand up. It was so amazing that we actually detected photons coming from this planet. It's very simple, right? It's not fancy. The gray points are the raw data. We had to bin it down a lot because there's a lot of noise in it. The black points are the bin down data. You can see how the brightness all of a sudden changes when you hit here. This is the secondary eclipse. The planet's going behind the star. And that little drop in brightness is caused by the absence of the heat from the planet. So we're observing this in the infrared. This is 15 microns. And that little dip means that it got a little bit cooler because the planet is blocked by the star. And so we can actually very clearly measure the temperature. The format of this figure was, I don't know if this was on purpose or not, but I think really inspired by the first measurements of heat coming from hot Jupiters from about 15 or 20 years ago, where we had similar quality data, but for planets that were 10 times bigger and 5 times hotter. And so it was kind of a nice nod to those early results that, we're doing the same type of pioneering measurement now with JWST for much smaller planets. Okay, enough of that, enough of my philosophizing. Here's the rating. This planet is really freaking hot. This is a 3 chili pepper, maximum temperature planet. This is the temperature relative to as hot as possible, 99% as hot as it could possibly be. I wrote up a news article about this after it came out. I thought I was really clever. I said, search for distant atmosphere, off to a rocky start. The copy editor liked it. My colleagues did not, because they were like, don't tell anyone there's no atmosphere. I was like, what do you think our job is? So, so this planet is, the first one we looked at looks exactly like a bare rock. So fine, we have bare rocks in the solar system. Mercury's a bare rock, no problem. Let's look at a planet that might be a little bit more likely to have an atmosphere. So this is now planet C. We started with the innermost planet because it was the easiest. It's also the hottest, though, and as you might imagine, the hotter a planet is, the harder its job is to keep its atmosphere. The atmosphere can escape, it can erode over time, and so going to these cooler ones might give us a better chance of finding one that does have an atmosphere. So that's what we did. Here it is. So this is a Venus analog in the sense that it's the same size and same temperature as Venus, but it sure does not look like Venus. So here is the measurement of the heat coming from the planet. Here's our data point compared to some models. You can see our planet is much hotter than predictions for a Venus-like atmosphere. That's the yellow, or a Venus-like atmosphere without clouds. That's the red. And so our naive first guess was that since this planet is about the same size and about the same temperature as Venus, it could be Venus-like. Venus has a lot of carbon dioxide in its atmosphere, likes to stick around, it's heavy, there's a bunch of it, it should be stable over a long time, but we're not seeing it. And it is possible that there could be a little bit of an atmosphere on the planet, but it can't be too thick and you can't have too much CO2, which was a surprise. It means that the atmosphere must have formed without too much carbon in it. And And if we're drawing really big conclusions from a single data point, you could say that if this planet is carbon poor, formed carbon poor with less carbon inventory than the Earth or Venus initially had, the other planets, the cooler planets in the system, might have also formed volatile poor. I said that to my husband, who's an actual data scientist, and he looked at me and he was like, okay, you measured this thing, and you're saying that these planets cannot possibly be habitable. I was like, yeah. What are you doing with your day? So this one I gave 2.5 chili peppers. It's not quite as hot as the innermost planet, but it's still way too hot to have a thick, carbon-rich atmosphere like we were first expecting. Okay, here we are. This is all of the planets that have been measured, accurate as of yesterday. There were actually 2 new ones that came out this morning. And here they are. This is showing the temperature relative to maximum. So 3 chili peppers would be 1 up here. You're 100% of your max. 2 chili peppers is in the middle. And a Venus-like atmosphere is down here, 1 chili pepper at the bottom. So if you draw any conclusion from this, it's that these guys are really not Venus-like. And already that's a bit of a surprise. I think for these hotter planets, Venus analog was our best guess of what they might look like, and that is not what they look like. Could you put any atmosphere on there at all? Sure you can. And it's a little bit of a Rorschach test for colleagues to see what they think when they look at this. Like, are they in the bargaining phase? Do they say, oh, like what kind of atmosphere could you put on there and still have it be consistent? And then you have the other ones who are like glass half empty, and they're like, oh, these are a bunch of bare rocks. But it's important that as scientists, we should keep our skeptical hats on, and we don't want to draw crazy conclusions when we only have a sample of half a dozen planets. And so I'd like to return to some wise words from my colleague Dave, who is the father of the transiting exoplanet field. This is what he had to say about it. So that's where we are. We've got about half a dozen planets that look a whole lot like bare rocks. We have also barely started looking, so this is early days. Sometimes the first things that we look at, because they're the easiest, are sort of the low-hanging fruit, which are not necessarily the planets that are most likely to have atmospheres. There is a ton of telescope time upcoming to make a bigger sample, to push to cooler planets. I think it is safe to say that not all planets are going to be like Earth. We're seeing enough, if you look at 6 planets and you got 6 of 6 that look pretty much like bare rocks, maybe, to return to our first question, is the Earth special? Maybe the Earth is actually a little bit special. It remains to be seen how special it is. And I think that JWST is performing beautifully. The astronomical community is all over this science question. If there are atmospheres to be found on these rocky planets, JWST will find them, but it hasn't yet. So with that, thank you very much, and I'm happy to take some questions.
Great, so thank you. We have time for some questions. So I'll actually start.
Sure.
So the stars that in the TRAPPIST system, that star is a what type star?
It's like an M9. It's like a very, very, very late M dwarf.
So those are much more active. And, could it have lost its atmosphere because of the stellar activity?
Yeah, I didn't get too much into these details, but there are some red flags that we were worried about for these planets with small host stars from the very beginning, because they tend to be more active. They're also very bright in the ultraviolet and X-ray in their early lifetimes. I know you know this, but I'm a professor at heart. And this contributes to substantial atmospheric loss from these planets. Depending on who you talk to, there's lots of ways around this. You might be able to store a lot of water in the mantle of the planet, and then it could outgas over time. Those are the bargainers. But yeah, I think this was a concern from the very beginning, that these small stars might not be good environments and that sun-like stars might be a better fit.
Good.
I saw a thing, years ago. This is David Finkelstein speculating how is it that Newton thought, or why he thought, that there was a photon or a particle of light. It has to do with being able to see stars at all. How far out are you going to be able to go looking at, scattering spherical waves coming off of, right?
Yeah, the short answer is not that far. So these planets are right in our backyard. If the galaxy is, call it 100,000 light years plus or minus across, these things are like 10 to 20 light years away. And even with a telescope like JWST, it's still a challenge. So I think that it will do everything that we can, but there are limits to how far away we can look.
On the Earth is special.
Aldous Huxley had an insightfulness and thought this might be another planet's hell. Do you have any thoughts on that?
My friend, I got to send you, across the street to the divinity school. This is so but to be not so flip about it, I think that a question that comes up very often about the search for life on other planets is how much we should presuppose about how Earth-like they actually are. And probably the universe is more creative than we are, and that whatever we think is a nice environment for life might, the universe might think very differently. So my approach is that Earth is a useful starting point as a reference, but that we should keep our eyes open about what heaven and hell might be on other planets.
You mentioned that you could tell planets tidally locked. Are these planets at TRAPPIST tidally locked at a M star?
Yes, these definitely are. So we can make a prediction for what the tidal locking timescale should be. It's very, very short for these planets. And we can also tell, by virtue of how hot their day sides are, that they must be locked. Because if they were not synchronously rotating, it would smear out that heat, and you get a much more even distribution of heat across the two hemispheres.
Yep.
So I'm curious, in your view, what's the outer limit of what JWST can do? Let's say optimistically we get a 20-year lifetime out of it. How many of these transiting, sort of Earth-sized exoplanets could you start to get temperatures for? And is there actually a prospect of getting, doing the next level of actually getting something about atmospheric composition if you find a hint of an atmosphere around one? Yeah,
great question. So I expect that we will be able to make measurements like this for a sample of 50 to 100, depending on how much telescope time we can wrestle away from the cosmologists.
They're doing the galaxies. So really.
Great. But to your second point of if we do find one that has an atmosphere, what can we learn about it? Quite a lot. So we can learn things like the surface pressure. We can learn the dominant chemical composition. So is it mostly methane or water or carbon dioxide or ammonia? What we won't be able to do is search for biosignatures. So that is a job of a future space telescope, and plans for that are already in the works, as you know.
Yeah.
How does it look like for planets with magma ocean and for them to retain a secondary atmosphere if they have already desiccated their first one during the first few million years of the M dwarf evolution. How does the secondary atmosphere retention look like for these planets? Because I think you mentioned they have like a hydrogen envelope on it. So how does it look like?
That's a great question, and the honest answer is I think we don't really know. So there is a huge potential to store a lot of water in these magma oceans. Water is really soluble in magma. But what else goes in there depends a lot on the details of your planet formation model, how much carbon you get, how much oxygen you get. It also depends on the time scale of the solidification of the interior of the planet. Depends on the rotation time scale. So I think I could find you a theorist who could make you a model, but I wouldn't necessarily believe what came out.
Is the habitable world observatory going to have something that the JWST doesn't that would help you out? Is there something now that's like advancing your abilities?
Yeah, that is a great question. Thank you for bringing this up. I ran out of time to talk about this, and I feel like I betrayed my field a little bit because we were all advertising this right now. So for anyone who doesn't know, the Habitable Worlds Observatory is a mission concept planned as a successor flagship mission to JWST. And it's going to have a very different approach from JWST. Rather than focusing on these transiting planets, it will be able to do direct imaging where you block out the light from the star, and you can actually take pictures of the planets in orbit around it. And this is the current state of the art. You can see four gas giant planets orbiting a nearby star. If you want to do this for an Earth analog and reflected light, you need a really big honking space telescope, and so that's the roadmap for the next 20 years. And scientifically, what this does is it moves us away from these small M-dwarf stars, which may be problematic for the atmospheres of the planets, and it pushes us to true Earth analogs that have sun-like stars.
Take one last question here.
So given the tremendous advance in data capabilities and confirmed exoplanets, does that change fundamental the Drake equation, or is the Drake equation still relevant?
Yeah, so the Drake equation, we're starting to fill in the terms. I think probably this crowd is fairly familiar with this, but this was an idea from Frank Drake about how to quantify the likelihood of intelligent civilization in the galaxy. And there were terms in there like, how many rocky planets in the habitable zone are there? How many of those have atmospheres? What the likelihood is for life to develop on those? And we're starting to fill in some of the terms. I think the last part of it is the likelihood of intelligent life, and this is not going to tell us that. But already it's a big step forward.
Terrific. So let's thank Laura for a fascinating talk.